We started this lecture by arguing that finding efficient algorithms on our own can be hard. We want to, if we can, reduce problems to things that somebody else has developed that are very efficient. And we've just seen a nice example of that. Because what we've just seen is that if we combine the idea of binary search with the idea of a divide and conquer for doing merge sort, that actually gives us a very efficient searching algorithm. In this case in particular, if we want to search a list k times, then the efficiency is n log n in order to do the sorting, plus k log n in order to do the search k times. And that, remember, we're comparing against something that is k times n. And so that says, boy, we're likely to be doing much better. If n is of any reasonable size, then the n log n times k log n is likely to be much smaller than just k times n. That still leaves the question of, can we do better? This is cool, but can we actually do better? And the answer is yes, and here we're just going to briefly highlight it. We're not going to talk a lot about this, but we want to point it out. Because in fact, Python comes with a data structure that supports very efficient searching, and that's the dictionary. You may have wondered about this because dictionaries are arbitrary collections of objects, and yet we can get things out very quickly from them. And the reason we can is that dictionaries use something called hashing. And a hash function is something that says that we can do a lookup in an amount of time that's almost independent of the size of the dictionary. Almost. But for most purposes, we can really think of it as saying we can do something that is really efficient, independent of the size of the dictionary. So let's just briefly talk then about what's hashing. The idea of hashing is the following. Given a key, that key into an element of a dictionary, for example, a hash function converts that key into an integer. And it then uses this integer to index into a list. That can, of course, be done in constant time. Right? So it says basically, when I've got a dictionary, I'm using that, if you like, sort of notion of indirection in a more complicated way. The elements are stored in a list, but to figure out where in the list to put them, I'm going to use this hash function to say, given the key, here's the location to go to. Now, conversion is done with this thing we call a hash function. And the idea of a hash function is it's going to map a large space of inputs to a much smaller space of outputs. Because it's doing this, it could, in principle, be a many-to-one mapping. What that means is it says, ideally, we'd like each input, each key, to go to a unique place in the output space into the list. But it's possible that two different keys could go to the same location in the list. When we do, we've got what we call a collision there. And there we're going to have to store, in fact, a little smaller sublist with each of those elements there together with their key, so that when I do the hashing, I will go to that location in the list, pull out that sublist, and do the search. Now, again, if I make the size of the hash table huge, I can reduce the number of collisions, but of course that chews up a lot of space. If I'm not clever about the hash function, I could have everything go to one space in the hash table, in which case I have the entire set of things there in a list, and I've lost because I've still got linear search. So what it comes down to is, and this is sometimes hard to do, we'd like to have a really good hash function. And a really good hash function has a uniform distribution. It minimizes the probability of a collision. With that idea, that I'm going to hash by computing some function on the key, that's going to tell me where in the list to go to, and I'm going to make the list large enough that I can store most of the elements in there, but not too large. One of the questions is, just sort of intuitively, how good is hashing? Well, if there are no collisions, then this is order 1. Now, that also assumes that the computation of the hash function can be done very efficiently, but let's assume that. It basically says, given an element, a key, I do the computation, I go straight to that point in the list, I pull it out, and if there are no collisions, only that element's at that location in the list, I'm in great shape. Flip out, of course, is if everything is hashed to the same bucket, then I'm stuck. Because now I've got order n, because I've got to then search through that list linearly to find the element I'm looking for. But in general, I could get something you can see could be very efficient. I can trade off space. How much memory do I use to make the hash table large? And then if I've got a good function, I can get close to uniform distribution, which reduces the complexity to something close to order 1. If, in fact, my hash table is big enough that it's likely that only one element gets hashed at any location, I'm at order 1. Even if it's not quite that, it's still pretty close because I'm not searching through a huge list there. I'm looking at 1 or 2 elements to find them. So in fact, what this says is there are even more efficient ways of doing search. It relies on finding really good hash functions. Python does that for dictionaries. And what we'll see as we move through the term is that there are other places in which we can use this idea of hashing to give us even better complexity. But nonetheless, the point of this was to say, if I can take key ideas, binary search, divide and conquer, I can use those ideas to create very efficient algorithms. And in this case, we did it for searching. And the second thing we've seen is that while the complexity of a single use of a procedure may be more than we'd like, we can sometimes amortize the cost. If we're going to search multiple times through something, the cost to do the sort is actually worthwhile because it gets made up by the improvement in efficiency of actually doing the search. And we'll see those ideas as we move through the term.